All right, so in a previous video we talked about our moments of inertia a little bit. And remember, our moment of inertia was basically just the mass of the object, right, times the radius squared. In fact, let me go ahead and put this. You guys are used to lowercase. I need to get used to that myself. Okay, so it's 1/2 times the mass times the radius squared. Now, for any moment of inertia, it's always going to be mr squared times something. For a disk, it happens to be 1/2. For a rod, it might be 1/12. A number of other things could be the case, right? For a sphere, it's 2/5. All these things you can find in those tables I'm going to put out there. But for a disk, let's think about a disk. So if you have a disk that is a uniform, a uniform density all the way through, like let's say this here, okay? So if you have a coaster, this is a disk, and we're going to assume it's about the same width the whole way through, same mass the whole way through. So this would have a moment of inertia of 1/2 mr squared. If you were moving it, rotating it about the center, that's very important. That center point is extremely important. So for a disk moving about the center, okay, if it's moving like this, here's your omega, right, your angular speed or your angular velocity is like this, then your moment of inertia for that would be 1/2 mr squared, because we're going about the center, okay? But what happens if you force it? Instead of rotating about the center, you decide you're going to start rotating about like an outside point. What do you do if all of a sudden your rotational point gets moved to there? Let's call it, I don't know, E for edge, right? So here's what happens, and here's how you calculate this. This may come up on AP, it's rare, but it does happen, okay? So if you need to figure out what the moment of inertia for this disk is on the edge, well, let's understand something first, okay? How did we get to the 1/2 mr squared? I'm not going to go through the calculus with you, okay? We can figure it out later on if you want to. You can ask Mr. Ellis. We'll get there if you want to, okay? But for right now, for the situation we're in right now, let's just think about it conceptually. This disk has uniform mass, right? All the way throughout it. It's the same material all the way through, so each little bit of it has the same mass per little unit area or unit, length, depending on how you want to look at it. If you're looking at a rod, unit length would be better. Same mass per unit length. For a disk, you've got more of an area kind of situation, so you have the same mass per unit area. So you have to get the moment of inertia for it, so you have to consider the mass. But if you think about it at the center, you're always kind of halfway, from the center to the edge, aren't you? So you get half, basically the mass, half the mass, and then whatever radius away it is, however large your radius of this disk is, it gets larger as you get a bigger disk, right? Whatever that mass is, that uniform mass is distributed equally out from the center point. So you get half as you go out from the center, okay? So your disk gets a 1/2 mr squared because it's going out from the edge, okay? But if we move it to this point here, how do we adjust for that and how do we account for that? We're going to use something called the parallel axis theorem to do so, okay? So how does this work? Well, this disk has the same density all the way throughout it, right? So what we need to do is figure out how far are we going to move it this way? Because now we've got to account for all the mass that's now hanging off the edge. That's what the moment of inertia really is. It's the amount of mass you sort of have hanging off the edge of the situation, right? The more mass you have hanging out on the edge, on a ledge, the higher your moment of inertia will be. So for this, if we're going to move this, center of rotation from here to here, it's going to start rotating about the edge instead of the center. We're going to have more mass hanging off the edge. So likewise, this number should get larger. And how do we figure that out? Well, here's how you do it. So for a disk only, okay? I of E, moment of inertia for the edge, right? Point on a disk, or for really any point out here. You could be here, could be there, whatever, right? It's going to be equal to the moment of inertia that you had for the center of the disk plus mass times, and if this is our R here, right? And I'm not even going to call it R. I'm going to call it something else. I'm going to call it D, the distance we displace it, right? The distance we move over. It's going to be m times d squared, because we're talking about an area, right? We're talking about something that has an area with a disk, okay? So if we move the center of rotation from here to here, or pivot points now on the edge, we've got all this mass hanging off the edge of the disk, and we have to account for all that mass, plus we have to account for basically all of the area that that mass is contained in. So we know mass per unit area, we can figure out how much mass is now hanging off the edge. And that's how you make your adjustment for a disk. Now let's go ahead and do that for a rod as well. Okay, so here we are. Will it erase? Hey, it'll erase now. Okay. So for a rod, about the center, the moment of inertia for a rod or a cylinder about its center point is going to be, so if we have our cylinder like so, right? If we're rotating it about this point, C, okay, the moment of inertia for that is going to be 1/12 mr squared. And r, again, is going to be the distance from the center point over, okay? But what if we don't want to rotate this thing about its center point? What if we want to pivot it, force it to pivot on the, edge, okay? If we move this center over to the edge again, or any point along there, this works for any point along there as well, right? We now have to account for that extra added mass hanging off of our pivot point, right? So how do we do that? Well, this is more of a length situation, isn't it? It's not more of an area. It's not really an area you have to worry about. It's more of a mass is divided up by equal lengths along the section of this thing. Each one of those little sections has the same mass, okay? So how you do this, and this is going to be involving a little bit of calculus to figure it out, okay? What you want to do is to find the moment of inertia for the rod about some other point, okay? You're going to have to do an integral. And you're going to go from, well, it depends on where you want to start at, but really it goes from the negative r over 2 to positive r over 2. I'm sorry, let me redo that. That is not true. I'm sorry. It is not r over 2. We want to consider the whole length of this beast, right? L, total length of this thing, okay? So if we want to consider the whole thing, we start out halfway through, right? So we have to go from basically negative 1/2 of it, okay, from here, all the way to figure out the total mass that is all the way to that other half of L, okay? So we got to get the total mass for the length of that rod hanging about the edge here. If you do something else, if you're only going, halfway through here, you can adjust these points, okay? So, and you're moving, the thing that's moving is your R, right? So you're moving about your R, so it's going to be with respect to R, okay? And this mass is divided up, your mass is the same per unit length of that thing. So that has to go in here as well, mass per unit length, okay? That goes in there. And what else goes in there? Well, the other thing that mattered was basically how far along here you were. So it was r squared, okay? So if you use this, you can actually figure out the entire moment of inertia for this thing, this rod. This only works for a rod on this one, okay? You can actually figure out the moment of inertia for a rod as you change your center point as you go out. So that's basically it in a nutshell.